Hello and welcome back to episode number 53 of the Piezo SHOCK Show. We are going to discover what are the driving voltage levels of an ultrasonic, let's get that grammar right, of an ultrasonic dental transducer. So let me go ahead and open up our video here showing the live camera. So here we have the ultrasonic dental transducer. So if you remember from previous videos, I broke open the transducer, the device in order to see the transducer. And here I spliced the wires and I put some new wires here from the transducer, so I can actually take measurements. So I have one voltage measurement, and obviously, how do you measure voltage? You put your voltage probe on one side and you put your ground on the other side. Well, in this case, there's no ground, but you choose ground whenever you want because this is a battery powered device. And it's still on. Let me just turn it off here. This is a battery powered device, so there's no wrong or right for where you put ground. But we also want a resistor here. I put here to measure the current, so voltage over the resistor. In this case, I put the resistor as 10 ohms, which is much smaller than the approximate 1 kilo ohm of the transducer itself. So with this, I can measure both voltage and current. I have both of these probes set at 10x, and here's my oscilloscope here. So this is a kind of a rough, and this is the device. So I mounted it back in its holder. And we have our tool fastened to the edge, and we're going to be taking a look at how this device actually works in practice. So let's go to actually the PowerPoint slide, and let me draw out for you the circuit diagram. So let's start with, we're not going to be able to see, I'll do white, and I'm going to be drawing with my finger today. That's not what I want. I want this. Okay. So we have our driving circuit there, and let me just change the thickness to match better what I'm trying to do. That's good. Okay, so we have our pen. So we have our driving surface. Our driving circuit or source. Then we have our transducers. So transducers are normally you can draw them as a crystal. So that's the designation for the crystal. And this is how you would normally have your circuit, your battery powered circuit. Maybe there would be some reference to ground, but there really is no true ground in this case. But there's usually probably a low side designation. This may be driven by a H bridge, in which case there is truly no definite ground there. Okay, so let's keep going. I'm going to be I put a resistor here. I could have put it here if I wanted to, but I didn't. So I put a resistor there, and this is 10 ohms, and I'm measuring voltage here. So this is channel 1 or channel A, and I'll just put that there. This is channel B, and this is where I'm putting ground. And there we go. So with this circuit diagram, that's what I've done when I spliced up the wires, and I showed all of this to you right here. Doesn't look that clean, and honestly, it doesn't need to be. Let's get it done. Let's keep moving. So without further ado, and I want to show you something here. We have these different settings. If you can read right here, there's a setting called soft, normal, middle, strong, and super strong. We're going to see what that actually does when you change the setting. So for example, you can start your device. Now you see the soft button is actuated. Now normal, middle, strong, super strong. Who came up with that? I couldn't tell you. But yeah, anyways, let's keep moving. So we're going to have different levels we're going to be testing. I'll be showing you what all those mean. And this practical device was just lots of fun to dig into and see how they actually designed it. Obviously, I can't reveal anything that my clients have ever done because that would be confidential, but I can take commercial devices already in the market that you can easily buy and show you how they work and why. So let's keep moving. let's go to the oscilloscope screen here. Right now, the device is off. Let's just do none. Just let it go so I can get a blank screen. So let me give you a rundown of what. Okay, so we have channel A in blue, channel B in red. B is the current measurement one, and I also have a green channel here, which is going to be channel B divided by 10, because those 10 ohms would give you voltage divided by resistance equals current. So that gives us all of those relationships. So we have voltage current. We have current set to voltage set to plus or minus 200 volts. And current just needs to be set at that range that correctly captures the voltage levels. And we have current calculated by the green channel, which might get confusing with channel C, but we're not using a channel C today. So that's okay. We're moving along here. So let's take a look at, well, what kind of signals are coming. So here, I'm going to start off. I'm going to press this button and turn it on super strong, or let's just start off with soft. Let's do some steady state analysis. So we have this coming up right on the screen. Let's do auto. Okay. And let's just drop a couple of measurements. And what measurements are important? And this is great that we get to look at this together. Okay, so let's do ACRMS for channel A. That's important. Now the picoscope is unique that it can do ACRMS and ignore the DC component. Your oscilloscope probably does not have that. Traditional oscilloscopes don't have it. They just have the plain RMS. So that's okay. Which includes your DC offset, but in this case, there shouldn't really be a DC offset, because it's, as you can kind of see on the screen, this channel A is symmetrical. That's okay. So then you shouldn't have any of that anyway. And for this sake, channel B will do its value. So it is running at right now 1.33 milliamps, which isn't very high, which does make sense with our previous measurements of the voltage and current. I mean, of the impedance of being a 1 kilo ohm there. Let's continue forward. So math channels. We need one more thing here. And what we need actually is channel A times, we need a current. Sorry, we need power, because you see these voltage waveforms are quite messy. It's going to be hard to determine what the meaning of voltage and current is in these circumstances. But power is that thing which is actually dissipated through your transducer. So I'm actually going to edit this. So channel A times channel B divided by 10, because of that resistor giving us the divide by 10 factor. And it's going to be in watts. This is perfect. So it's automatically going to be there for us. Let's just make sure that we can get that on the screen. It's getting chopped off, so I kind of have to redo that probe here. I think I made a mistake in how I was editing it. Override automatic range selection. Let's leave that off. Okay. And I will now increase the scale so we can actually see something going on there. Let me reduce that a little bit. So we have voltage. It was a channel A, current there. And we don't need to do that. So this is perfect. I'm also showing you how to set up your oscilloscope to make these measurements, which is just great. And we have to take the DC, basically DC average of channel of the watt waveform, which is channel A times channel B divided by 10, which gives us all the right units. And we have the milliwatt value as shown on the screen here. So we have a device operating at, and make sure all the current probes and everything are all connected, all good and square. So we have this. We have 40 volts, and this is the resting power. Now this video might get a little bit long, and we have 1.33 milliamps and 25 milliwatts at 40 volts. This gives us a quite, and again, just to take a look at what's happening. We are running on soft. There's a transducer there, and everything is square. So let's go into Excel. I'm going to stop the transducer. Oh, the last thing I forgot to tell you is a frequency. Because this is not a transducer we've designed, frequency is not obvious. We're not controlling the frequency directly. So the best place to get frequency is from the voltage waveform, which is channel A in this case. We can just add a frequency measurement and see that the frequency is in fact 36.6 kilohertz there. So that's perfect. I can't just copy all this out, but I can type it up. Isn't that a charm? Okay, delete that. It's a charm, it really is. So let me just stop this and scroll over so I can see the average values. So voltage, current, power, frequency. Now I warned you that frequency is going to be changing on us because of the way this is designed. And current is 1.343 milliamps. I'll note that's milliamps later. And 25.89, which is right there, 25.89. And that obviously changes depending. And the current is the frequency is 36.59. And because it's a kind of a square-ish wave, you can tell frequency pretty well. And this is soft. Now it's still running right now, so I expect these values not to be changing much. Let's see what happens when I kind of when I push down on the transducer. Hopefully we have enough juice in the battery to finish the video in a nice way, but if not, we'll continue later. So now I'm going to be touching down on a surface. Let's see if it's actually working correctly. The way you can tell that is you hit it against something metal, like this screwdriver here. You can hear a noise. Yeah, it's here making a noise. Let me try to put it closer to my microphone and see if you can actually hear it. Okay, so that you may have been able to hear that. You can definitely hear if I had touched the screw here. I mean, I can feel it, hear it, and feel it. I know it's working at least. That's great. So let's just look at what current does and voltage does when I kind of load this guy up. And let's okay. I think I should reduce that screen. Bring us back here. And that. And kind of bring it over. Resume share. I think pause. Okay, so we are back. Let's see what happens again when we load the transducer. So now so if you remember, our watt level is 25 milliwatts, 36.59, and 40, and so we have actually about the same. So 25. Let's look at power as the main medium. So 25 milliwatts, and let me just better voltage RMS, milliamps RMS, milliwatts, and kilohertz. Those are all the right units. So this is a soft setting. This is setting. When we load the transducer, lo and behold, we have more current. Actually, we have the same amount of current, about. We have much more power. Now it's 45 milliwatts. So it's not exactly going in the same location when I'm touching. It's not returning to the same power level, but the current level is remaining similar. So you can see if I touch I'm touching the screw right now. You can't exactly hear it because the microphone I'm using is a headset. So it's kind of bouncing and increasing in terms of watts. I don't think there's no frequency control, closed loop frequency control, because, well, if you take a look at a if I'm really loading it right now, I'm really loading it against the table right now, pushing down the transducer on the table, and it's not changing frequency. And you see the load. It seems like it's getting closer to the resonant frequency because the way I am when I'm loading it, the watts are increasing temporarily at least, and then they're decreasing. So when you do load a transducer, like let's say this was the impedance, frequency. Let's go back here. And I can draw with my finger, which is nice. I have a plot here, impedance and frequency, and we have normally this plot there, and let's say we found our resonant point to be, we took a sweep and it found the resonant point to be there. When you're loading your transducer, the resonance the minimum impedance spreads out. It becomes wider, which then brings the surrounding impedance lower, because a high Q factor is sharper. A lower Q factor leads to a little bit wider response, but the neighboring impedances do drop as a result, and they are able to dissipate more power. So in this case, loading can actually increase the power dissipated by bringing us closer to resonance, and that's why the power would increase. When power increases, we take that as a signature of being closer to the resonant point, especially. Okay. Right now it just turned off. There, I turned it back on. Okay, so that was cool. Let's see what happens when I change the setting from soft. Let's wait for that to happen. So when now it's on soft, I'm going to press this button and go on normal. Okay, the voltage is at 55 volts. Let's do snipping tool. This makes things easier. I can actually stop this too. So it's basically 55 volts. If you want to just follow along how I would do an actual experiment. So soft, and now it's on normal. So we have values. I'm just going to copy these values down, honestly. 55.7 volts. Current is 1.669 milliamps. The milliwatts is 41.38. And the frequency here is 36.59. So it's keeping that same frequency. I'm going to show you how it's going to change. I'm only going to copy voltage and power for next time. So I'm going to increase the, let that go again. Okay. So now it changed to about 60 volts, which is always great when things change on you. You can tell this is not the most stable driver output. And then when I increase it again, it's at 70, it's about at 80 volts. And when I increase it again, it's at 94. So it's 80, then 94. Let's go all the, okay, this is at soft. This is the lowest level. 50, I'm gonna remember this in my head, 50. The next level is 65. The next level is 80. The next level is 95. Now super strong, 115. It's going up 15 volts every time. And I'm going to turn it off. And at 15 volts, and I'm going to stop it because I want to copy this because this is the strongest behavior. So it was approximately doing this: 40, 55, 80, 95. Let's just call it like 115 or 115 or so. So soft. The technique for this device is when you want to increase power, it's not increasing current. middle, strong, and super strong. And for this case, it's using values here. So let's just write out what exactly is 120.1 volts, 2.441, and the power is 98.38 milliamps. The frequency is still 36.6. So this is just increasing power as you go. The impedance seems kind of small. A little bit surprised about that. Yeah, it says impedance is 30,000 ohms. That is hard for me to believe. It seems like I may have done. Let me see if I did an error with regards to this measure. No, both probes are on 10x. Maybe this is a 100 ohm probe. Sorry, I know if it's 100 ohm, it'd be even less. Yeah, I would look to double check that if I had more time. But I think also because the waveforms are like your square waveform, and you have a very distorted current waveform that may be problematic. You may actually want to just concentrate on this power value and this voltage value. So that would be pretty valuable. A way you could calculate the interim impedance from a 2040 volt power source. So, we can, one second, let me just get that calculation out. I forgot it. Yeah, I just forget little equations like that. So the power equals V squared over R. So power times the impedance, or the effective exact in phase impedance, if you were to make some resistance, you could say power times resistance, the square root of power times resistance. Well, we're not really looking for, so VRMS squared. So we can go VRMS squared divided by power equals the resistance. That could be a better way. V squared divided by power. I'm sure it's not going to give us a really big value, but and that's milliwatts, so multiply by 1,000. So that did not give us any smaller value than the other one did. It's still like, oh, it's 146. Well, I'll have to get back to you on that one. But yeah, this impedance certainly seems a little bit off. But anyways, that's how you would go about doing the values, and you would double check them as you would. Let me just make sure I had this as 10x. I had this as 1x. I had this at 1x. So indeed, if you did have it as 1x, bro, it's going to be 10 times larger. You know that sound you make when things don't go the way you thought they should. So all these are 10 times. This is like divided by 10. So everything should be 10 times higher. Life is a little bit closer to normal. So instead of 30,000 ohms, it's like 3 kilo ohms, which I believe for 40 volts. So if you remember, the original value at lower voltage was almost a kilo ohm. So a 3 times voltage increase as you get to with higher voltage, so normal to have 3 times voltage. Now you're thinking 10 times, it's gonna be way too much. And this multiplied by not by 1,000, but you multiply by 100, so 5 kilo ohms. So you go from 3 to 5 as you keep increasing the voltage. All of this makes sense. You're not also not operating exactly at the resonant point. So this is all making sense to me. Whew. All right. You got to make sure. Sometimes it's really useful to just like measure a current, measure like a resistor or something, just to tell you you're operating in the space, in the realm of real, instead of what the heck. Operating in the land of what the heck is not the funnest thing you can do. Okay, let's continue. I want to show you guys one last thing. So I showed you that this is a constant voltage device. Each time you increase the power level on the hand, you're actually increasing the voltage, which is an effective way of increasing power delivery. I also showed you. Let's see. Let me just show you for the super strong case where it's. Let me get you this back to super strong. Yeah, where's my mouse? Oh, mouse. That's that. And I think I also need to decrease this scale here to better fit the screen. And I think I also need to go up 1 volt. Yes, so we have a current of this. Let's just try loading it and see what happens. The current, the present power is almost 1 watt. It's almost an active 1 watt. I don't want to edit the measurement. Thank you. The current power is 1 watt. I'm going to touch the nail and see what happens. It's like 700. Oh, I got shocked. Ouch. Okay. Anyways, that was 115 volts to my finger. Okay, so the power increases. So it seems like it's locking onto a frequency below the resonance. Hence why you're increasing. Actually, see if you see current is about constant. That probably has to do with the drive voltage, the drive circuit, keeping the current quite constant as you load down the transducer, because you see the voltage change as the impedance gets lower. So if the voltage changes and the current stays the same, impedance is dropping. That means you're getting closer to the resonant point and power is increasing, and it's all part of the game of life. Okay, now I want to show you something cool. Let me stop this. Also, I'm going to stop my device here by holding the power button, which turns it off. I want to show you one last thing, and I'm going to get rid of all these measurements here. Delete. Now I'm going to do a single. I'm going to increase this to 100 to 200 milliseconds per. I don't know how much this is going to give me, but I'm going to try to get as many samples as possible. This is the way you trigger. So I'm going to trigger right there at 40 volts, and I'm going to turn it on, and you obviously see that's just stuck there. So now I'm going to turn on my device, and I'll show you what happens here. This whole part is a frequency sweeping regime. If you see here, this is frequency sweeping happening, and trying to find the resonant point. I think it statically, each of these sections is actually stepping through a different frequency range. I don't think this oscilloscope is going to be accurate enough to actually find it, but let me just actually show you here. Okay, I'm going to stop it. I'm going to stop my device here too. Okay, and I'm going to start my signal again. So it's running. I'm going to recenter my screen. And I'm going to turn on my device. And this is what, this is kind of interesting. So I will actually, so look what's happening here. It sweeps the frequency across different bands. It seems like there's 2 resonant points here. There's 1 resonant point there. As the voltage goes down, there's actually a resonant point. So I want to actually pull up the spectrum mode on here. And right now the device is on, so I'm going to turn it off. Actually, I'm going to turn it off, please. Okay, thank you. Then I'm going to, I guess, decrease that a little bit. I want to just set some settings here. I want peak hold, and I want let's do a linear scale. This is a spectrum mode, okay? And 200 volts is fine. So peak hold, that's okay. Let's just keep on Blackman. We can just. I don't think we need to increase these, but we could. Let's see what happens. Usually with spectrum, you just got to play around with it once it starts. So now nothing's on. So it didn't trigger yet. I have it triggered at 40 volts. So I turn it on. Okay. Okay, let's just make sure it actually triggers. And I think we do need to go down to this range down right there. It is hunting for frequencies in this range. So I might just actually zoom out and do that. So I'm just going to continue to do this. And let me just increase this all the way. It's all the way to the max. Okay, good. So start. So right now it's on. So it's obviously just going to have a peak there. And it's a single trigger. So it's a single. So it's not going to keep on moving, but let's just turn this off here. So I turned it back off. Now I'm turning this on. I want to capture that sweep. I might not be able to do it because just how the timing works, but it's worth a try. Okay, what happened here? What did I catch? I caught a lot of activity in the 30 kilohertz range. I believe this is going to give us, and let me just stop it. I'm going to try this just like one or two more times, then I'm going to actually stop and just tell you I was looking for a wider peak here, but it is I guess I could do just repeat, or I could do auto. I think repeat would be better and turning it off first. So I turned it off. I'm putting on, it's on repeat now. And peak hold is also on. Ah, got it. We got that. So now I wanted to, I think a black top or a flat top would just help me out better. I'll stop it. Start again. Yeah, so it's doing some type of, I'm going to just keep doing this again and again. So I get some good stuff out of it. I'm continuously pressing the button, turning it off so I get different sweeps. But basically, it's sweeping frequency and it's doing it kind of fast. I wonder what 2 megahertz consists of 2 milliseconds. I think it. Let me see if that actually converts when I go back and forth. And it doesn't. But anyways, that's okay. So you did see in this view that I had, you did see these values of this wider band frequency sweep. Let me just turn it off. Turn it on again. So you saw these. It would be a lot more smooth. I think probably if I used, no, it's not going to work. If you do higher frequency, it'll probably churn faster. Let me see. Turn off. Turn on. Yeah, it's still not doing it as fast, but that's okay. We can also do it from here. Now I'm just beating the bush here. I'm just kind of beating around what I need to be doing. I'll actually just do a single and run it. I'm turning it off. I just want to capture something a little bit better, and then I'll turn it on for you guys. And then I can actually add a value, add a view spectrum. This sometimes ends up being better than doing it otherwise. So add a spectrum, and I do want to, with this spectrum, let's make it linear peak hold. I wish it showed me values that I could change. I forgot how to do it. Logarithmic. Ooh. No, wish it had a little bit linear, logarithmic. It does show some type of like, I don't think it's the right, what I'm looking for exactly. Nonetheless, I think these are frequency steps where this is sweeping a frequency, is looking for a certain current, and then it's changing each of these little values here, or each of these little stepping points is where the frequency is changing, and that takes a little bit of time. And the point where the voltage is the lowest is going to be the resonant frequency. You can also tell this. This is very cool actually. Let me show you something, guys. You see here initially how when the voltage, so it sweeps this frequency over here, and when the voltage turns off, you have like a little small voltage, like the piezo is ringing down, it has very small voltage. However, when you're at the resonant frequency, the driving voltage is lower, the driving voltage is smaller, like the actual driving part here. It's smaller because you're driving a higher impedance, lower impedance, so it's taking more current. But when you open that voltage back up, now the piezo is ringing without being at the right frequency. Therefore, you have this big boom here of voltage when you're right when you're finishing and your current's decaying out. So those are pretty cool things. I think next time we're going to really dig into the driver. I'm just not sure yet. I don't know if I'll do some characterization. I might just do more driver stuff, and then eventually we're going to characterization, and eventually we'll get into driving this thing all by ourselves, which is this fun. This is great fun. So next time we're going to get into looking at the driver and how that works. It's a pretty small device. It's very compact. We're producing 100 volts out of out of a battery. I don't know exactly what. If there's some voltage conversion here, but it's battery powered and it's cheap and it'll be fun. This has been episode number 53 of the Piezo SHOCK Show. I hope you enjoyed it. I think it was very useful, good learning experience. And what driving voltages of an ultrasonic dental transducer of this type? It is 45 volts to 120 volts. And we work up from powers from 250 millivolts, 250 milliwatts, because this is remember I got this all missed by a factor of 10 because I didn't set the probe to 10x, which I did in practice, but I didn't. So multiply by that by 10. So we have 250 milliwatts to 1 watt of actual dissipated power in the transducer itself, and it doesn't change much when you actually impact. And you actually, it seems like it locks on a little before the resonant frequency, based on what I've seen here. So you've been watching the Piezo SHOCK Show again, and feel free to subscribe to this channel. Also look in the description for links to my consulting services. I run a business. I serve folks developing ultrasonic transducers and their driving systems, and and everything around that. So contact me if you need help there. But I will look forward to seeing you in the next video. Take care.